kind of pretty elementary stuff last time to sort of set the stage. We talked about heat, which is just a measure of the motion of atoms. You know, you think of pool balls. We use the analogy to pool balls, and the faster they are moving on the table, we called that temperature. It's not a perfect analogy because the pool balls are made of atoms, and there can be a hot pool ball. You know, you just pull out of some boiling water and set it there on the table, and it's not moving at all. Its atoms are moving quickly, even if the pool ball isn't. But for atoms, the only question is how fast the things are moving. That's the only manifestation of its temperature. It doesn't have a temperature, you know, sort of independent just of the motion of those atoms. And we also talked about light, which is a self-propagating wave of electricity and magnetism. So there's only one speed of this disturbance at which the way it evolves in time kind of reproduces itself, you know, a second from now or 10 seconds from now or whatever, where the wave is self-propagating. So just like a wave on water, there's a certain speed that it wants to go, and if you tried to make it go faster, it would probably break or something like that. Light is the same way. It has to be at that speed in order to kind of perpetuate itself as a sort of disturbance. So we talked about heat because that's, you know, what global warming is primarily about, is heat. And we talked about light because the only way really to get heat in and out of the Earth system from space, which is what, you know, we're talking about doing, is by light, because you can't conduct heat through a vacuum or convect through a vacuum. Those things all kind of require matter to carry the energy, and the only way to get energy across a vacuum is by light. So the question now is, how is it that the light interacts with matter? I mean, it seems natural to us that you go out in the sun and it's nice and warm, and so you feel that it does. It's, you know that sunlight can warm you up, but it doesn't, you know, necessarily have to be that way. Another form of energy actually that comes out of the sun are these little particles called neutrinos, and they basically don't interact with matter at all. They go right through the Earth without slowing down. It's very hard to measure them or detect them. You have to have big tanks of I don't know, Clorox bleach or something like that deep in coal mines in order to detect an occasional neutrino that comes through. But for the most part, neutrinos don't interact with matter. And it could have, you know, been just as well the same way for light, that it could have not interacted with matter. But it turns out that it does. And the way it does is mostly by means of the electrical part of the light. So we have this propagating oscillation in the electric field. So just voltages that you could measure with a voltmeter if it was fast enough, plus and minus. And this is traveling through space, and then it hits some piece of matter that has an electric charge, a positive or a negative electric charge. And let's say that piece of matter, we'll sort of idealize it, but we'll say that it's like a weight on a spring that's attached to something, and so it can vibrate. So if the light comes in and it's vibrating, if the frequency, remember we said that frequency is written by the Greek letter nu, and it has units of cycles per second, or if we want to be kind of a little bit more opaque about it and, you know, abbreviated, we could also just say units of seconds to the -1, because -1 means it's on the bottom of a fraction, and they oftentimes ignore the cycles part. So units of frequency you might see in units of per second. This oscillator also has a characteristic frequency that it likes to vibrate at, which is determined by how heavy the weight is and how strong the spring is. So if it turns out that the frequency of the light is equal to the frequency of the light is equal to the frequency of the oscillator, then it can be absorbed. So that means that the energy from the light hits this thing, and it gets this thing to vibrating harder, and so it's increasing the temperature of that oscillator, because the more energetically it's oscillating, vibrating, the higher its temperature. And so the light can get absorbed by making that thing warm up. So mostly it's the electric field that interacts with matter. There is an exception if you've ever gone to get an MRI at the hospital, like if you've broken something or whatever. In that case, they have this really intense magnetic field, and the magnetic field actually interacts with matter, and that's how they can tell, what's going on inside you. But for the most part, the way we interact with light is by the electric field. So one aspect of this that is important and will be important later on in particular is that this is a two-way street. So if the frequency of the light matches that of the oscillator, the matter can absorb light. But also, if you've got this oscillator and it's got some sort of vibrational energy to it, it's got some temperature, that came about because something bounced off of it and clobbered it and started it to vibrate or whatever, this thing can emit light. So it turns out that just about any form of matter that has a temperature that's higher than absolute zero is going to be emitting light. And stuff that's at room temperature, we can't see the light that it's emitting. We can see colors from it, but that's reflected light off of the visible light, from the lights. If we turned off all the lights in here, it would just be dark. There'd be no, light coming from these objects. But that's only because we can't see in the infrared. At room temperature, the light that stuff emits, the energy is low enough that the light that it emits is in the infrared. And if we had eyes that could see in the infrared, we could see that. An electric burner on the stove, when you turn on the electricity and let it heat up, it starts to glow red hot, right? So it's actually making light. You turn off the lights and you can see that thing glowing in the dark. It turns out that burner is also emitting in just the same way at room temperature, only we can't see it because we don't see in the infrared. We only see in the visible. So let's say that we have an object that has oscillators at all different frequencies. This is called, there's a name for this, it's called a blackbody. So if we were to draw a picture of it, kind of analogous to that picture, let's have a wall, and then we'll have a bunch of different weights, all of which have charges and are on springs. And the springs have all different lengths. So, one of these oscillators is going to play one note, and then another oscillator is going to play another note. It's like one of those African thumb harps, or musical instruments are kind of this way. So, an object that have oscillators at all different frequencies is called a blackbody. And then the light that comes from such an object is called blackbody radiation. Or the blackbody spectrum. So you can use physics to calculate what you expect the spectrum of light to be from a black body at some temperature. And we're not gonna do the calculation because it's kind of beyond what we want to get into here, but I'm going to show you the results of what you get if you do that calculation and sort of what goes into it, what comes out. Because it turns out that the black body spectrum was the trigger that changed physics, in a very, very profound way around the beginning of the last century. It sort of gave notice that Isaac Newton wasn't the whole story, and that there was this whole new world of physics that had to be kind of worked out. So I'm going to show you this not because it's absolutely essential to dealing with climate change, but because this is sort of a general education science class, and we're here, and this is an amazing thing, and so we're just going to check it out for a couple of minutes. So the spectrum of light, what we're looking for is the intensity, how bright it is, as a function of the wavelength. That's what a spectrum is kind of a graph of how bright it is as a function of the color on the x-axis there. So what goes into the calculation we're assuming that because it's a black body, the matter has all of the notes, the frequencies, and there's none of them missing. And we're also going to assume that average energy that is sort of stored in each of those notes. Remember we talked about last time different modes of motion of the atoms in a molecule all store the same amount of energy on average. And that amount is equal to 1/2 K times the temperature, where K is a constant you can look up in a physics book. It's a Boltzmann constant. You don't really have to know what it is exactly, but just the idea that at some temperature, all the different ways of vibrating or rotating or flying around or whatever are like little batteries that sort of store this thermal energy, this motion energy, and they all store the same amount on average as this 1/2 kT. So if you take those two assumptions and you calculate what the spectrum of light from some object should be, it goes like this. It blows up is what it does. It starts out kind of low at low frequencies, and then as the frequency gets higher and higher, you're getting to kind of scarier and scarier kinds of light. So low frequency light is sort of infrared and microwaves and radio waves are down there. And then visible is somewhere at shorter frequencies and higher energies than that. And then you go further and you get to ultraviolet that gives you skin cancer, and ultimately you get to X-rays and you get to gamma rays. And what these assumptions lead you to is the expectation that as the frequency that you're measuring gets higher and higher, the intensity of the light gets higher and higher. And so the total amount of energy that is emitted by this object is given by the area under the curve. And you see that the curve, keeps going. So the area under the curve is infinite. And so it's predicting that this piece of chalk should be absolutely killing us all with X-rays and gamma rays and radiation and horrible things like that. And it should be putting out an infinite amount of energy. And that's totally wrong. What you actually measure, if you measure the intensity of light coming from some object, the classical prediction doesn't look too bad at the beginning, but then it kind of stops like that. So this is measured. And this is calculated. So this sounds like kind of a bad day for scientists, right? To get the answer so profoundly wrong. This discrepancy is known. A lot of times these sorts of problems get names because people talk about it. Scientists at a meeting, sitting in a bar, say, well, what do you think about this? They need a name to talk about these things. And the name for this discrepancy is the UltraViolet Catastrophe. Not, Simpson's problem or the, Blackbody paradox or anything kind of mealy-mouthed like that. Catastrophe. That's how severely this thing, misses the mark. So when you're, trying to work out how things work in science, if you make a prediction and then you measure something and you've got it right, that's sort of good news because you can use the theory then to predict things, about the future or different things that you can't measure or something like that. It doesn't necessarily mean that your theory is completely right. It could be that you're getting the right answer for the wrong reasons. Newton is a great example of that because he didn't have all this quantum mechanics, which is where we're going to, and yet he still got the right answer because in most situations, his approximation to physics works just fine. But if you end up with a mismatch like this and the theory just fails, that's actually kind of an exciting thing in science because it means that there's something going on in the real world that isn't in your theory. And so that means there's something to learn. It's sort of a harder row to hoe because it's harder to get papers published or grant proposals or whatever because everybody can say, oh, you don't know what the hell you're doing because look how badly you miss this. It's kind of, it's uneasy time when things go like this, but it does mean that something is there to be found. It's an opportunity. And the solution to this ultraviolet catastrophe is a theory of physics called quantum mechanics. The idea of quantum mechanics is that energy is not a continuous thing, but it comes in chunks, which are kind of like non-subdividable. It's sort of like water coming out of the tap looks like a continuous thing. You can pour yourself, it would seem to us, as tiny a glass of water as you like, and just divide the water up even more and more. You could cut it in half, forever and make smaller and smaller drops of water. That's sort of how it seems to us, and that's how energy seems to us too. But water, it turns out, is made up of molecules, and so you get to some point where you have one molecule of water, and you can't divide that anymore. Water is coming in chunks, and energy is sort of that way too. A counterpart, sort of the flip side of the coin in quantum mechanics, this very strange theory, is that matter comes in waves. So stuff like electrons that have mass, you know, and they seem to be discrete little things like this little rapidly diminishing piece of chalk in my hand here. They seem like they are chunks, but they also have sort of this wave character to them. So what I'm going to do for the rest of today is sort of just tell you kind of what this is like, so you have a sense of this, because we're sort of at this historic place where we've found the ultraviolet catastrophe, and here's the answer, and it's just an amazingly weird phenomenon. So it bears sort of thinking about. So the way that quantum mechanics leads to the blackbody spectrum is because of the first part of this, that the energy is not continuous, but it comes in chunks. And that includes the energy of the vibration in that oscillator. So this is kind of weird. It's as if you go to the playground and you're pushing a kid on the swing, and you can't push the kid to any height on the swing, but only, you know, sort of like this or like that, but nowhere in between. It's like a volume knob on a stereo or something that has little clicks on it, you know, that you can only turn it up to. I mean, that's just a stylistic thing, but you know, a swing set at the playground doesn't seem like there's any sort of clicky things in it. That's because they're very close together. We're not able to perceive it. But the vibrational energy of atoms and molecules comes in these chunks, and it turns out that this can be important. So the size of the chunks of energy in the oscillators, delta E, we'll call this the chunk size, is equal to a quantity h nu, where h is just another constant that you can look up in a book. It's called Planck's constant. And nu is, of course, the frequency of the oscillator. So if we make a plot of energy as a function of the frequency again, the same axes as we were doing for the spectrum, down here, this is sort of a small frequency, and so the chunks, which are given by the frequency times this constant, will be sort of small. So the energy levels down here are very close together, like that. You know, they get so close together that you might as well just call it a continuum, because, you know, we can't really tell the difference even. But when you get out to very high frequencies, like the X-rays and gamma rays that we were so afraid of coming out of this piece of chalk, the frequency is high, and so that times this constant gives you a big chunk size, and so the energy levels are very far apart. Yes?
Can you explain that again?
Yeah, so I sort of pulled this theory out of, you know, thin air, this formula rather.
No, I mean, why are they further apart?
Because the frequency, this is a high frequency, a big number, and, you know, so it's many, many, many beats per second is what frequency is. And so if you take a big number and multiply it by a constant, you get a big number, whereas down here this is a small number. You take that and multiply by the same constant, you get something that's relatively small. Thank you for asking. I encourage you to ask questions. It's bravo. So where are we? So we assumed when we were doing the classical calculation, the guys who were doing this, the physicists, the people who were doing this, assumed that all of the oscillators have an energy equal to 1/2 kT, because that was a formula that I sort of pulled out of the air last lecture, and since it was last lecture, now we all believe in it, right? So they should all have on average 1/2 kT of energy, because they're all like these batteries. And so let's draw in 1/2 kT of energy and say that it's right there. Now, if we were to warm that up and change the temperature, you could make 1/2 kT be bigger. You could have it be anywhere you want to. But let's just say it's at a temperature that puts the thermal energy sort of right there. So that's how much these oscillators have on average. And you can see that the low frequency oscillators, such as will make stuff like infrared light, like this piece of chalk is actually shining, the chunk is smaller than this thermal energy, and so there's no problem. So on average they have 1/2 kT, so some of them may be a little low and some may be a little high, and they're jumping around all the time from lower to higher energy, and that's what they have to do if they're going to absorb and emit light. So to emit light, you have to start from sort of a higher energy and then drop to a lower energy state, and then you give off light. That's sort of where the light comes from. And that all still sort of works because the chunks are small enough that classical physics is not such a bad approximation. So what you end up with is a black body spectrum that at low frequencies kind of looks like the classical prediction. So we'll have frequency and energy again. And so here's classical. And then here's observed. And you see that at low frequency, the classical works pretty well because the chunks are small enough that they don't really mess things up too much. But when you get to the really high energy stuff, the UV from the UltraViolet Catastrophe and all of that, the energy chunks are so far apart that basically it's like saying that the average among all of us in this room is each of us has, on average, we have $1 in our pocket. On average, that's how much money all of us have. And if we had, all that money was just in pennies, then, everybody would have like 95 cents or, $1.25 or something like that. And we'd be trading pennies around. That would be sort of the analogy. And that would sort of work as if the money was, some continuous thing like a glass of water you can sort of pour around. But if I tell you that on average everybody in the room has $1 and the only form of currency allowed is a $100 bill, well, then you look around and you know that 2 people in here have $100 bills and everybody else has nothing. And so the number of sort of transactions of people giving each other and taking money will be much less because basically most of us are too poor to have any money whatsoever because the only form of money is this enormous $100 bill that you just can't afford. It's kind of that way for the ultraviolet and X-ray frequency of oscillators. The chunks are so big that basically none of them, very few of them are excited, and so there's no energy going in, coming out. And so the spectrum looks like the classical when the chunks are small, and then it sort of clamps down. Because quantum mechanics clamps it down. Quantum mechanics is the solution to the ultraviolet catastrophe. Does this make sense? Yes? The question is, how does the energy being in chunk lead to black bodies? The energy being in chunks leads to a change in the blackbody spectrum. If classical mechanics was right, if that's all there was, the blackbody spectrum would look like this. And in fact, it looks different. It looks like that. And so where we're going to go with this, starting in the next lecture, is you change temperature and suddenly some oscillators that were out of reach before become within reach. And so this thing sort of moves over this way as you change the temperature. It's all controlled by quantum mechanics. But for now, quantum mechanics is the reason why this thing stops instead of going up into the ultraviolet catastrophe. And we'll leave it at that for now. So I want to tell you just a little bit more about quantum mechanics. I just used quantum mechanics to solve this problem that we had. And so, before you go away all happy. Oh, yes, another question.
I have a question. It's not really about quantum mechanics. It's sort of about neutrinos and blackbody radiation, or rather black bodies as it relates to the dark matter. I was just curious because you said before that so matter absorbs light or emits light. Is it possible to make than other black bodies like dark matter to emit light even though they absorb it?
I don't think they know very well what dark matter is.
Well,
So neutrinos might be part of it. I don't know if I can answer your question. I don't really know. We're sort of going off into realms that I'm, walking on thin ice here. Yeah. Okay, so quantum mechanics. There is a whole field of discussion which is known in sort of official circles as quantum weirdness. Quantum mechanics is incredibly successful at predicting all kinds of things that can be measured, but no one knows why it should be this way, and it seems it's got implications that are very, very weird. Einstein always hated the idea of quantum mechanics. He had this famous quote, "God does not play dice with the universe." Well, it turns out apparently God or whomever does play dice with the universe. Quantum mechanics is right, Einstein or no Einstein, but it's very, very strange. And so I want to describe one of the manifestations of quantum weirdness by explaining to you an experiment, a diffraction experiment called the two-slit diffraction experiment. So let's say we have a light source and it's making light, which I'm going to draw sort of like I would draw water waves on an ocean, where you draw the high parts of the waves, and so the waves are spreading out in a circle like if you dropped a pebble into a pond and the waves would spread out. And we're going to have it go through and hit a wall that has two holes in it, two slits. And so we're now going to have two waves that are coming from those two slits, and they're in phase because they're both got their source back here. And then we're going to have a screen here, and we're going to measure the intensity, how bright the light is that hits there. So if I draw this carefully enough, let's say that the screen is right there. If we look right at this point, we've got the crest of one wave from one slit and the crest of another wave from another slit. So it's like we're taking one wave that's like this and we're adding to it another wave that's just the same, and what you get is a bigger wave. So this is called constructive interference. So if we move a little ways up this screen, we'll get to a point where you have the crest of one wave from one of the two slits, and it coincides with the trough of another wave from the other slit, and you combine those, and what you get is flat. They cancel each other out. So this is destructive interference. So this is all classical mechanics. You can do this with a pan of water and you know, make waves with some kind of an oscillator or something bobbing up and down and see all this. So you should be able to visualize what's going on here, that the waves add up in constructive and destructive ways. Nothing weird yet. So we're going to modify the experiment now. And we're going to have some sort of an electron gun that shoots electrons out into a vacuum and into this whole thing. And they're going to hit a screen that has two holes in it, two slits. And they're going to then hit a screen behind where we're going to record where they hit. So you have electron guns in the old cathode ray TVs. If you have a TV, you know, from your great-grandparents or something that's, you know, kind of fat, not one of the skinny ones, that's how these work. They fire electrons, and then there's a screen that lights up, where the chemistry is such that it lights up when the electron hits. So that's how CRT computer monitors and TVs work. So we fire these electrons through, and then we sort of pay attention to where the electrons hit. And what you get are bright bands and dark bands, just like with the water waves. So this is now starting to get a little bit strange, because these electrons are, you know, solid chunks of matter. They're like cue balls or something, and yet they seem to be canceling out. What we see in these dark and light bands are constructive and destructive interference. So that's pretty weird, because electrons have mass. So two electrons coming together, do they really somehow annihilate each other? Einstein said, and he's not wrong about this, that E equals mc squared. So you could take the mass of the electron and multiply it by the speed of light squared, and you get a huge amount of energy. So you don't expect electrons to just annihilate each other. And yet somehow there is this sort of wave character to the electrons. Even though they're particles and they have mass and you can bounce them off of things, they seem to have this wave character, so that electrons from one going through one slit and from another can interfere with each other and make each other, you know, focus where each other goes. So that's extremely strange, but it goes to the sort of wave character of matter. So it's like the flip side of the coin of quantum mechanics. Energy comes in chunks, particles come in waves. So then the third step in this experiment is to slow this electron gun way down. So we're just going to fire one electron at a time. And so it goes and is completely done before the next one goes. It's just one electron at a time, and then you keep tabs on where they hit, and after you've shot a bunch of electrons, you find the same pattern. So one, it still interferes. So this is now getting, you know, even stranger, because not only do you have to have two electrons kind of annihilate each other or interact in this weird way, But a single electron, which can only go through presumably one slit or the other, is somehow going through both slits and then interfering with itself. So this is really weird. And what you do now, because you're just so totally freaked out by this goofy result, is you put some sort of a sensor to measure. So I'm going to draw a sort of schematic of a sensor as just an eyeball, but it's probably some, electronic sensor that you can put that will measure whether an electron goes through this slit or that slit. Because you want to see what's going on. You can't believe that it's going through both, or if it's doing that, you want to see it. So you put that sensor there, and what happens now, all of a sudden, is you measure either it goes through one or the other. Electron sensor. You find the electron goes through one slit or the other, not both. And you also find, which is kind of the height of quantum weirdness, that the bands disappear. So you didn't change the experiment, all you did was look at it, but somehow you changed the fundamental nature of that electron. It was a wave before when you weren't looking at it, which meant that it did this interference with itself, but as soon as you look at it, it does what is called, there's a name for this. It doesn't mean we understand why it's doing it, but it's just a name. The name is collapsing the wave function. So this is a sort of a dogma almost. It's called the Copenhagen Interpretation. Not the Copenhagen theory or explanation or anything like that, just interpretation. So it's like a religious dogma almost, really, because it's not really explaining anything, it's just putting words on it. What the words say is that when you observe the particle, the ghostly waveness of the whole thing collapses and it becomes a solid chunk of matter again, just by sort of looking at it. So there was an alternative theory for this, just to show you how weird this is, called the many worlds hypothesis, which is that the whole universe splits into two completely separate universes, just like on the old science fiction, on Star Trek or something like that. When you make an observation, you commit yourself to one or the other universe. And it's crazy, but it fits the explanation, it explains things just as well as the Copenhagen interpretation. So it's profoundly strange, sort of unsettling physics that we have had to resort to explain things like the blackbody spectrum. Okay, so I will see you on Wednesday. Good luck finding the lab.